Okay, so I have a few examples for you on when you use calculating friction. So none of these are super difficult, so we'll be able to go fairly quickly, but I didn't want to end up with a video too long or YouTube gets mad. So, example number one, what is the coefficient of friction, static friction, if it takes 34 newtons of force to move a box that weighs 67 newtons? The first thing to notice is that in a problem like this, they give you the weight. Now you know that when we talked about the equation for the coefficient of friction, that it doesn't involve weight, it involves normal force. But let's think about it. If it's a box sitting on the ground, assuming that it's level ground and they don't tell you anything that would give you a hint otherwise, the weight equals the normal force. So you'll see a lot of problems like this. So they give you the normal force, and they're asking you in this case for the coefficient of friction. So remember, you'll either be asked to solve for it, as you are in this case, or you'll use it in a problem and it will be given to you, but you never have to memorize it or come up with that constant from another source, because it depends on the two surfaces involved, and there's a near infinite, combination of surfaces you could come up with. And also, I didn't mention that it depends on the temperature that's going on at the time. So there's a lot of factors involved in these coefficients. The situation has to be just right for the constant to be a constant. So anyway, in this case we're just going to solve for it. So we know the normal force and we know the friction force. I could have put Fs on this one since it's static, but I just generalized and used Fr for friction. So here's our equation. We put our numbers in and we divide out and solve for the coefficient. Notice you have newtons over newtons, so there is no unit on the coefficient of friction. So there's a pretty simple example. So we'll go ahead and look at another one. So example 2. So in this case, they give you a push force. The box takes 350 newtons to start moving when the coefficient of static friction is 0.35. What is the weight of the box? So again, when they refer to weight, what they're really asking you to do is solve for the normal force, since the normal force and weight are equal unless it's on a ramp. Could you do these on a ramp? Absolutely. Will we? Probably not. We might save that for AP Physics to work out. But you could. It's just not something we're going to take the time for. So, in this case, we are looking for the weight, so that means we're finding the normal force. They gave us the coefficient, and we have the push force, which it says that you have to overcome 350 newtons to start a box moving. So that would be your static friction force. That's the force that you're overcoming in order to get it going. So, here's our equation again. Put in our numbers and divide both sides by 0.35 and we get the normal force. Oh, 1,000. That's a nice even number. It's always happy when you have an even number when you solve a problem. So that's all you do on that one. So that's a pretty quick example. So example 3. And this one is slightly more complicated, although it's really not bad. Let's say we have a car and it has a coefficient of friction between the ground and its tires of 0.85, no units. What is the mass of the car if it takes 9,620 newtons of force to make it slide along the ground? So you're pushing a car. That could happen. Your battery dies. That's not good. So we're going to push the car. We're looking for how much mass the car has. What is the mass of the car? So first we're going to find the normal force, and we're going to use our friction formula to do that. So we know the friction force is the 9,620. And we know the coefficient of friction, so we solve for the normal force. In this case, they asked us the mass, so there's only one other thing that we have to do. We know that mass and normal force will be the same on a flat surface, so that is actually the weight of the car, the 11,318. So to get to the mass, you need to divide by 9.8. So I take my F equals ma equation. I could have put F equals mg because specifically the acceleration is due to gravity, so it's 9.8, and I solve for the mass there. So that's a different example. The last one that we'll do will be one involving a two-body problem. So this one is slightly more tricky. So this is actually exactly like the two-body problem we did before. I think I even used the same masses and everything. The thing different is that we have friction involved. Now you'll see this a lot. They won't tell you there's friction in this problem, there's not friction. They might just give you mu k equals this or mu s equals that. And since you're a good physics student, you know when you see a mu that you have friction. So that's the giveaway here. So given the constant 0.33, I'm going to put in my force diagram the idea of friction. So it's the same force diagram as before. Friction will resist the motion. Is there friction on block B? No, because there's no surface for it to go on, and we always assume that pulleys are frictionless, so there's no friction there. So whenever there is friction, we're talking about on the table. So if it's a regular Atwood machine, the kind where you just have a pulley and two masses, you will not be solving for friction in those kind of problems, just in these modified Atwood machine situations. So there's our coordinate system. So remember, the positive direction follows the string, which is the direction of the motion. And there's our other force diagram, which is exactly the same as before. So no friction to deal with there. So question goes back to find the acceleration. So we do this just like we did before. That's exactly the same. The only difference is now we have an FK in the problem. So the first thing we have to do is actually solve for the friction force, because they didn't tell us what the force was in the problem, just the constant. So I take the given constant times the normal force. So when we did this problem before, we actually didn't even solve for the normal force because we didn't need it. But when there's friction involved, you do have to find out what it is. So that's going to be 98 newtons. And we solve for the friction force there, and you have negative 32 newtons. Notice the negative doesn't show up in the problem until I put it there, and I'm doing that because I define my coordinate system in the direction of motion, and the friction is against the direction of motion, therefore it's negative. Okay, so now I'm going to go ahead and find the weight of the hanging block. That's the 49 newtons, so that's the pull force. So when I look at my net force equation, I've got the weight of block B pulling the system, and I have the friction force trying to resist that pull. So that's why it's the difference between those two forces equals mass times acceleration. Notice again the mass is both of the masses added together. You can't just do one when you find the acceleration of the system. So I break out my calculator, I do the math, and I find the acceleration there. Okay, so that's the only thing you do differently when there's friction, is you have to calculate it and then subtract it from the pulling force. And from there on, we'll practice all the problems that we did before, adding friction in, and that's really it for the chapter. So the whole chapter is Newton's second law. We put in Newton's third law in this, which requires no math. Everything else is mostly problem solving. So look forward to a test soon. Good times.